following is an introduction to using the ODT code. We'll go through obtaining the code, building it, and describing some of the layout of the cases, and then going through a quick demonstration of executing the code. First thing we need to do is obtain the code. So in a folder called ODT in my home directory, I'm going to install it there. First I go to the code repository on Bitbucket, log in and grab the link for the ODT code. Then we'll type git clone and then that link, it will download the code into this local directory. Okay, and then inside ODT 2.0 there's the following directory structure. So this has directories build, data, doc, input, post, run, and source. They're mostly self-explanatory. Build will contain all the make files. All of the data that comes from a run will be put in the data directory. Doc is documentation. All the input files for various cases are in input. Post is where codes for post-processing go. The run directory includes the executable as well as some run scripts and sources in the source directory. So the first thing to do is to go into the build directory. The code needs to use YAML library, and we've included the YAML code as part of the ODT code. For convenience, if you already have YAML, you can link to those libraries separately. So we build it by just running build.yaml.sh. build.yaml.sh, and we won't wait for it to complete. Instead, we'll just copy. What we'll do is once that finishes building in the source directory, it will make a folder called YAML. So let's get rid of the one that it started building, and we'll just copy in an existing YAML folder in there. Okay, so when you build YAML, it creates this directory called YAML in the source code. So if we go back up to the build directory, we have a make file, and then we have several make dot some extension, FSL, Mac, Spark. So if we look in the make file, at the very top, there's if not defined the match variable, then match will be whatever we define it to be, Mac. And then it's going to include the file called make dot whatever that variable is. So it could be make.match, make.fsl, make.spark, make.whatever computer I happen to have. This is just a way for us to put all of our system dependent settings in our own file called make.whatever your machine name is. So on my computer, I might use make.mac. If we look at that, we have make.mac. There we specify some compiler flags, some directory, or some code directives. Then we have some compile options, the name of the compiler. In this case on my machine it's G++, and the C compiler is GCC. And then we also specify the location of Cantera. So you'll need to have Cantera installed on your computer in order to compile the ODT code. On my computer, it's located here for the library and the include files. So these are the things that are specific to my computer. So I would go in the make file and set match equal to Mac, and then it's going to include that file with all its settings up here. If you're working on a different computer, you could create your own make.mymachine, and then in the make file just change this match equals mymachine, and it'll include the correct file. Alternatively, when you run make, you can type match equals whatever you want, Spark, and then it will include the make.spark instead. So once we've set that up, we just type make-j8. The J8 just speeds it up, it runs it in parallel. And the code compiles, and then we'll link. Okay, and then if we go up to the run directory, we can see it created a file called ODT.x. That's the executable that it just created. So it built fine. Now, if we go back up to build, in the make file, there's several options. There's make all. There's make clean. If you want to clean up the source code, make the documentation. Make depend can create dependencies. Make YAML will create the YAML files. So a few different options there. Okay, so let's go back up and look at how to run an example. So if we go into the input directory, we can see there's several test cases already created for us. And if we wanted to create our own test case, we just make a new folder for that. Most all of these are ODT cases, except for Flamelet, FLMLT, and HIPS. Those are for the Flamelet version of the ODT code and the HIPS version of the ODT code. So we can see here a RT for Rayleigh-Taylor. We have an axial annulus flow, a channel flow, channel scalar, cold jet, cold propane jet, jet flame, piloted sitting jet, pipe flow. So if we go into, for example, the pipe flow, then the main input file is called ODT_input.yaml. And for use with Cantera, we'll use an XML file for chemical reaction, and we've named that not used because for pipe flow we don't need to use a Cantera chemical mechanism file. So ODT_input.yaml, if we look at it, it's a YAML file. We can see the different parameters that are set. Most of these will have the variable name, the variable value, and then a documentation string here as a comment. So all the different parameters in the code. There's the boundary conditions, and then at the bottom are dump times. These are times at which the code will output data values. Obviously those will be between 0 and t_end, which is the end simulation time. So if we just look through a few of these parameters, especially some of the ones that we change often, seed is the seed for the random number generator. If you're running, normally you'd want to randomize that seed so that each realization is different, but for repeatability you can specify it to be some number that you want. Put a negative value here, like -1 or something, to randomize that seed. T_end is how long you're going to run for. The domain length is the size of the domain. Pretty much everything in the code uses SI units, so meters, kilograms, pascals, etc. End grid 0, this is the initial number of grid points. This will be used as you specify the initial condition, and the code is adaptive, so it will quickly adapt the number of grid points based on the profiles. Row 0 is a density that's used in some places for the eddy selection process. It doesn't refer to the actual density in variable density cases, although it does refer to the density when using cold flow cases like we're using right now. The kinematic viscosity is kvisc0 is given here, and it has the same meaning as row 0. We have a pressure gradient, dpdx, -2.0 is the pressure gradient applied to system pressure, a mechanism file. And we have a problem type, here it's a channel flow. The ODT parameters for Z, A, and C. We have a large eddy suppression type, so here we're using a fraction of the total domain length. We have the and then the parameter for the large eddy suppression. Sometimes in papers this is called beta. Diff CFL is a multiplier for the time step, so if you want a smaller time step size, you adjust that right here. Which solver we're using, there's explicit, semi-implicit, or string, some boundary condition types. The C chord tells us whether we're a planar, cylindrical, or spherical ODT simulation. GDENS is a grid density factor for the mesh adapter. We don't have to change that very often, but if you increase that value, it'll give a higher grid resolution. although the adaptive mesher automatically sets a finer mesh in regions where it's needed. dxmin will be the smallest grid size, and notice that it's normalized by the domain length. So if you increase your domain size, you'll need to, or decrease your domain size, you'll need to change dxmin accordingly if you want to keep a constant grid size. dxmax, and then some ODT parameters, pmax, paverage, a few others. We don't change these that often. Mod dump is a factor. This means that we will write an output file every 10 eddies. So if you don't want to see an output file if you wanted to see an output file after every eddy, then you'd make that 1. If you never want to see output files for eddies, just make it large, and then you can select, and then it will only output the dump times. So in other words, you'll get an output file specified dependent on mod dump, and separately based on the dump times that are specified. So we'll put this down to 10 for now. Then we have some boundary conditions that are given. So this is the input file for a pipe flow case. Okay, so then it's the input directory. If we go to, let's see, let's look at the run directory. So the executable is called ODT.x, and there's some helper scripts for running the code, because and those are called run one realization, run single realization, which is currently out of date, slurmjob.sh, and slurmjobarray.sh. So these two are for use on clusters when we're running parallel simulations where we want multiple realizations run. Slurmjob.sh will use the parallel aspects of the code, which are implemented using MPI, and slurmjob will use the array features of Slurm. So for now, on a single machine, let's look at run one realization.sh. Basically what this does is it's a bash script. It outputs the start time, and then the user would specify the input directory. So we have in this case it's specified to the hips, but we want to run a let's see, we wanted to run the pipe flow. So if we go up into .input pipe flow, okay, so come back over pipe flow, run directory, run one realization.sh, and we can change this to pipe flow like so. Okay, and then there's a couple of functions given. We'll look at those in a second. And then at the bottom we have run case test. So this is the test is going to be the case name, and the case name is going to be so in the data directory it will create a folder called test where all of the files are written. So you can call this whatever you want. And run case is the folder, so case name is going to be test. So basically it goes into the directory. If test is already there, it's going to delete that folder, so be careful with that. And then it's going to create a new folder called test, or whatever you name it. And then it will, inside of that directory, so you'll have data/test, you'll have a subdirectory called data, input, and runtime. So data is where the data is going to go. Input will be the input files, so you have a copy of the input files, so you know exactly what was run. And then the runtime is where runtime output is stored in a file. Then we're going to just copy the input files into the input directory and any restart files that are needed. Then we just echo to the screen that we're running. And then the ODT code itself is simply run by giving it a parameter for the case name, in this case test, and 0 for the realization number that we're doing. So on a single processor, we'll want to run realization 0. If we're running multiple realizations in parallel, then each process would have 0, 1, 2, 3, etc. to indicate to the ODT code which which realization it's doing. And this will be convenient for separating the results of the realizations, as we'll see in a moment. So this script can be run with a -r flag. So you can see at the top, run it as /run1.sh or /run1.sh-r, and that'll just rebuild the code in case you're debugging. That can be convenient. In that case, you don't have to go back up to the build directory, make the code, go back to run, and then execute the code. So it's just a little bit faster. And then finally, it just echoes the end simulation time and finishes. So if we run this, /run1, so if we look in the data directory first, you can see that it's empty. So if we go /run1realization.sh, and maybe we'll give that an ampersand to run it in the background, then we can see it's running. If we go up to the data directory, we can see now there's a test folder. If we go inside of test, there's a data input and runtime. If we go to the runtime, we can see that the runtime output is being is listed there, tail-f runtime, and we can see the code actually running here. So that's probably enough. We can just quit here. You can see 2,000. Well, let's look at the runtime. So the header here, EE, time, etc., are given in the following. So this would be eddy event number 1 occurred at the following simulation time, which gives us the time since the previous diffusion event, the number of eddies that have been tried, the number of grid points in the simulation, the eddy size, the eddy position, the eddy acceptance probability, the number of eddies that were tried that were possible, the average acceptance probability, and for this eddy, it's inverse timescale. So that's convenient information, and we can see that we've gone up to 84 eddies that have occurred. So if we go up the directory, we can see, if we go into the input folder, we can see we get the input for this case. In the data directory, we can see the data _00000. This is for realization 0. If we had multiple realizations that were done, maybe 200 realizations, then we'd have 200 folders where the data for each realization would be specified in its given folder. So if we go into this data folder, we get lots of files because we said we wanted to see a file every so many eddies. ls pipe word count. We've got 1249 eddies that occurred. So we get data files for the initial profile, and then the initial profile that's been adapted, and then this tag here is just we're seeing the results after an eddy has occurred and after we've adapted the diffusion process. There's also a plot.odt.gnu file for convenience in plotting GNU plot data. And then we've only got one dump time because we only ran long enough to see that one dump file occur. Okay, so if we look in one of these full files, ODT11520, the structure of the data file, we get the time, the number of grid points, the domain size, the pressure, and then we have columns for each of these variables, the grid point position, the face position, the U velocity, V velocity, and W velocity. So depending on the case, we might have many more values there. So if we want, we can plot these things. So one thing that might be convenient is it's set up in a way that's convenient for use with GNU plot. So if we type GNU plot, we can do plot ODT12120 using 1,3, and we'll get a profile which will, so 1:3, this means plot column 1 versus 3. That's going to be pos versus uvel, and we can see the y-axis is uvel and the position on the line is given. If we wanted to step through this and watch the evolution, we could do ODT star.dat can see all those data files. We can dump those to some GNU plot file, p.gnu. If we edit p.gnu, see all those data files. Let's see, we'll put that one at the beginning, and then we can issue the GNU plot commands. Use 1.3, pause, -1. Okay, so we can specify those GNU plot commands. That's enough. Okay, and then we can go back into GNU plot and load p.gnu, and this will let us basically step through the evolution of the jet. So maybe for convenience, let's put in a range set y range 0 to 25. So we can see the increase due to the pressure gradient of the velocity profile, and we can also see the eddy events as they occur based on the ones that we've currently output. So that's fairly convenient. Okay, so if we go into the post directory, we have a pipe flow case here, and there's some existing Python files. If we look at statspipe.py, it'll compute things like the mean and the RMS profiles for velocity. And basically, we're going to do things like create mkdir. So we run this thing by typing statspipe, Python statspipe.py, and then the case name. In this case, it would be test, like so. And and if we look at this, then we can see we're going to go up. Case name is that first argument. We're going to make a directory data case name post. So this will create in our test directory inside data a post directory, and that's where we'll dump the results of the post processing. Then it'll go through and do its calculations. Part of those calculations are going to be reading the data files that are in there. So it's going to read data test data realization 0, and then process all of those dump files, for example. And you can set up your post-processing scripts any way you like. Okay, if we look up in the doc directory, we can see, so if we just look at documentation online.html, we can see the website here that holds an online version of the documentation so that you don't have to make it. And if we go to that documentation, ignite.byu.edu ODT 2.0. Okay, so here's the documentation of the code, and it kind of goes through a description of what we've done, building the code, explanation of input files, case setup, running the code, post-processing. It also discusses some general code structure, which we won't talk about here, and a style guide, rules to follow if you want to edit code. Also, there's a couple of documents for ODT code theory and laminar flamelets, etc. The documentation is all built with Doxygen, so you can see, any particular file you want to see. It'll show you the class structure as well as the member functions, data members, and you can go in and actually look at the source code if you want to see that as well. Okay, so that concludes this first introductory discussion.